Welcome to this video about Linklist, defined as list class in the Java Collections framework. In this demo, I'll examine how a linked list behaves when adding or removing an element at a specified position. These are the three methods implemented in Linklist that I'll discuss. The same method actually as in the ArrayList demo, since both classes implement these methods defined in the collection and list interfaces. First, a two-parameter add method which inserts the specified element at the specified position in a list. Then a one-parameter remove method which removes the element at the specified position in the list. And finally, a clear method which removes all the elements from a list. This is a sample code. In the main method, I start by creating a linked list object and filling it immediately with 4 elements. Next, I'll add an integer constant 310 at position 0, so completely before all the other elements, and an integer constant 320 at position 3. Then I remove the element at position 4, so the 5th element, after which I completely clear the linked list. Executing this whole program will provide following output. Let's find out in a memory layout what happens when executing these statements. I start here where I left off in a previous demo. So local variable nrs pointing to a linked list object containing a size of 4 elements. And the 4 elements were added during the construction of the linked list, passing 4 values 2, 10, 20, 30, 40. So the construction here is the same as where I left off in the previous demo. Property first referring to the first node at fictional address 2000, and last to node at fictional address 2300. And we clearly see all the nodes linked to each other via the next property to the following node. And the address is always noted at the bottom. And via the previous property in the opposite direction. In addition, each node contains an item property pointing to the actual integer wrapper object that we have added. And so printing this list will show the 4 elements. Okay, let's now add integer 310 at position 0, so at the beginning of the list. As explained in the previous demo, first an integer wrapper object will be created here at fictional address 3050. And the reference to that is then passed to the add method, which I show immediately here. Together with the index, the position at which we want to add the element, 0 in our case. So the stack frame is set up for the add method. It's an instance method, so we have the this pointer. Then parameter index with a value of 0 and the reference to the element that we want to add. Then a check if index equals to size. In other words, if we want to add the element at the back, then invoke link last, which was the case in the previous demo, but not now. So link before. But before actually invoking link before, we need to specify before which node the new node must be inserted. And that is determined in method called node, to which the index is passed. So stack frame for the method called node. So we have first this pointer and our parameter index with a value of 0. Now, in order to determine the node we're looking for at position index, we could start looking from the beginning or the end of the list. This is what the if statement is testing. Basically, if index less than size 1 bit shift to the right, which comes down to a division by 2. So size is 4 divided by 2. So if index with a value of 0 less than 2, which is the case, so we jump in this branch of the if statement. We declare local variable x in the stack frame, which is initialized to the value of first 2000. So x will refer to the first node that was ever created, and this is our starting point when iterating through the list, looking for the correct position. Now in our situation, so this is done using the for, a new variable I will be allocated on the stack with position 0, and we need to iterate until I less than 0, which is already true. So actually we don't have to iterate at all through the list. We will do so in a next scenario. So x remains unaltered, which is the return value of the methods, and it is before this node at address 2000 that the new node will be added to the linked list. So we leave the node methods, but hold on to this address because we are in the process of actually invoking another method, the linkBefore, which is what we're going to do now. And the first argument is the element. It's actually the integer wrap object holding value 310. We want to add it to the linked list. So now we invoke the linkBefore methods, set up the stack frame. So the first value is this pointer. The next value is the first parameter e, referring to the integer object, and then the successor, that was this value 2000, our first node. This node will represent the successor of the new node. Then a new local variable pred, and I think this is actually a syntax error in the JDK and should be previous because it represents the previous node. So new variable, let's stick with the pred, which is initialized to successor.previous. So successor 2000.previous is this one, null. That's easy. Then a new variable new node will be declared on the stack, and its value is, well, that's what I've explained in the previous demo. So I'll not jump to the code, but show you the end result. So a new node will be created on the heap at fictional address 2400 and will be initialized with pred, e, and successor. So my local variables pred, e, and successor. So passing them via the constructor comes down to the previous property is null, the item property is 3050, and the next property is this value of 2000, the successor value. Then the assignments to the new node variable. New node is address 2400. Then we need to reset a few pointers. First one is successor.previous is new node. Successor.previous, which was null, now needs to point to the new node. So here comes the value of the address 2400. Okay. Then if pred is null, which is the case, then first the property of my linked list object is new node, because the first object is not this one anymore, but this one. So this value 2000 will be overridden by the value of new node, which is 2400. And here we have set the reference. Last thing we need to do is increment the size to 5, and that's it. Our node has been added. We leave the method, clear up the stack frame, and go straight back to the main methods. And voila, our node has been added all the way at the beginning, position 0, with a value of 310. And if we start at this node, the next property will refer to the second node. And as first node, we are being referred to by that node as well via its previous property. So the chain has been extended with a new node. Printing the elements. So we start with the first, okay, value 310, then via the next property to 10, via the next to 20, to 30, to 40, and this is what is printed out. What about the performance? The big O notation. Well, adding an element at the beginning when index is 0, or at the very end when index equals to size minus 1, that is an O1 operation, because it always comes down to the same thing. Let's now add an element somewhere in the middle at index 3. So first a new integer wrap object at fictional address 3060, then not displaying the code this time, but recall from the previous insertion that the first thing that must be determined is before which node the new node is to be inserted. This is done by iterating an amount of times starting from first or last until we find the node before which we need to insert. And in this case, it will be this one. Position at index 3. This is 0, 1, 2, 3. So before the node at address 2200. So after determining the node before which we need to insert a new node, it was the linkBefore method that actually created a new node, and we're going to initialize the properties immediately. So the previous will be referring to node at address 2100, the item property to the integer wrapper object, and the next property will be this node. And then in order to be really part of the chain of nodes, 2 more references need to be adjusted. The next node that the new node is referring to must refer to the new node via its previous property. So this value must be overwritten to refer to the new node, and the previous node it is referring to, its next property must refer to the new node as well. So this value will be overwritten, and we are now part of the chain of nodes. One last thing is the size that must be incremented to 6. And voila, node using value 320 has been added to the linked list at position index 3. What about big O? Adding an element somewhere in the middle comes down to the same operation, apart from having to iterate to the correct position before being able to add a new node. So this iteration is size dependent, but less than on, so quicker than ArrayList. How about removing an element at position 4? Let's run through some code again. So the remove method is invoked, setting up the stack frame, the dis pointer, and index 4. This method has a return value for which we reserve some space. Then the unlink method will be invoked, but first of all we need to determine what must be removed. So using the same node method we've seen before in order to determine the position of the node. So we invoke the node methods, set up the stack frame, so the dis pointer, and then the index of 4. And this is the same method we've seen during the first scenario of adding an element. Here again, do we start to iterate from the beginning or from the end? Which one is quickest? If index with a value of 4 less than size divided by 2, size is 6 divided by 2 is 3, so is 4 less than 3? No, so we jump to the else branch. A new variable is allocated on a stack frame x, which is initialized to last, and last is the address of the last node 2300, so this one. So we have a reference to the last node, and that is where we are going to start and iterate. Then I variable, we start at size -1, and we're going to iterate an amount of times. First of all, we're going to change the x value, x.previous assigned to x, so the previous is 2200, so this value will be overwritten, and we are now with the previous node. We decrement the I, and we stop iterating because we have found the node we want to remove. This will be the return value of the method, so this is the node to be removed at address 2200. We leave the method, we clear the stack frame, but hold on to the address of this one because we're going to pass it immediately for the invocation to the unlink method. Set up the stack frame, the dis pointer, and then the value of x. This is the node we're going to remove. So all references to it must be diverted. And this is what the remove method does. Now the implementation displayed here is not 100% of what you'll find in the GDK. It is similar. Logically, it does exactly the same thing. First of all, by declaring a new local variable element, which is initialized to x.item, x.item 3030. So element will refer to the integer wrapper object. Then the first reference that has to be diverted is x.previous. This one dot next, this arrow may not point to this one anymore because it will be removed, but need to point to this one. So this value will be overridden by x.next. X.next is this one, 2300. So this value will be overridden by 2300. And that's it. And then a similar thing for the previous. Then x.next dot previous, this arrow, so pointing to the node to be removed, has to be diverted and will receive the value of x.previous, which is x.previous, which is 2500. So this value will have a value of 2500 because we need to refer to this node. This is done now. Okay. Then the outgoing references from the node to be removed will be set to null. So x.previous, this arrow will be set to null. Same one for the next, null. And then a reference to the item, again, null. And the size will be decremented to 5. The return value of this unlink method, which is a reference to the integer wrapper object. We're going to leave the method, first passing the return value to the previous method. Clear up the stack frame, and we're back at remove, returning immediately. Now I'm not going to do anything in the invoker, in the main method, but know that the return value of the remove method is actually a reference to the integer wrapper object to which the deleted node was referring. So just returning, clearing up the stack frame, and we're back at the main method. And we see now the deleted node, no references to it, nor any references leaving from it. So the garbage collector will eventually remove this. And if we print out the 5 elements, we see that this node with 230 has been removed. Finally, the clear methods. What happens with the clear methods? I jump immediately to the clear methods. So the this pointer, no arguments, an x variable allocated in a for loop, initialized to first. First is 2400 is this one. So new variable 2400, and we're going to start here, and then for each node we're going to clear up everything. Then with the local variable next, referring to x.next. X.next is the next node, 2000. That is the next. Okay. Then first of all, we clear everything of the node we are referring to via x. So the item property, the next property, and the previous property. Null. Then we refer to the next node to be cleared, and we continue to do so all along the chain of nodes. Now I'm going to leave the for loop immediately and show you the end results. So everything will be set to null. Finally, the first and the last must be cleared as well. Okay, and all references will be removed. And finally, the size is set to 0. We leave the clear method back at main. We see that our linked list has been cleared. What does it mean? No nodes anymore linked to each other. Size 0, first is null and last is null. And this is an on method as well, because of course the more elements in the linked list, the longer it takes for this operation to complete. So to resume for linked list, the add method. If adding all the way at the beginning or all the way at the end, it is an O1 operation. If somewhere in the middle, that takes some time, but it is still quicker than adding an element with an array list if a resize takes place. Then with remove less than on, so quicker than array list, but on, because we need to iterate to the proper position, and the clear of course is on as well. Okay, that's it for this demo. I hope you have a better understanding about add, remove and clear, and thank you for watching and for pressing the like button if you appreciate this video. See you.